Okay, so we're going to just review some of the key inferential procedures that you've seen in simple linear regression, right? So inferential methods are basically confidence intervals and hypothesis testing. So these are the assumptions in a regression model. We'll actually go into these in a lot more detail in module 3. So statement A is actually a weaker version of statement B. So truth be told, if I really wanted to be, if I could have actually struck these out and just use statement B. So as I kind of mentioned, that statement B is basically a stronger version of statement A, right? So statement B is saying that your error terms independent and identically distributed as a normal distribution with mean 0, variance given sigma square, right? So mean 0, that's where this statement is. Variance sigma square, which is constant, that's where that is. And if they are independent, then the covariance is 0, right? So statement B is a stronger version of statement A. And we'll talk about in module 3 how to assess these assumptions. But these assumptions are present because it then allows us to at least have a mathematical basis for a lot of these formulas that we see for the confidence intervals and hypothesis testing. So just as a recollection, right, what the goal of a confidence interval is that it provides a range of plausible values for the unknown parameter of interest. So in simple linear regression, typically that's the slope. Right? Usually we're more interested in the slope than the intercept because the slope informs us, right, how does y the predicted y change as the x variable changes. Right, so that's why we are more interested in this. So general form of a confidence interval, the statistic plus or minus the multiplier times the standard error of the statistic. Collectively, right, this term is sometimes called the margin of error. Right, so so for the slope, this statistics typically is the sample slope. The multiplier is based on the distribution, so we know that the distribution associated with the slope, estimated slope, is the t-distribution. Standard error of the statistic, sometimes we'll just write it as standard error of beta 1 hat. So the confidence interval, right, is given over here. So I kind of just wrote that in the previous slide. So that's the estimate, that's the multiplier, and that's the standard error, and collectively, that's the margin of error. Degrees of freedom in simple linear regression n-2, it's actually given by n-p more generally speaking, where p denotes the number of parameters in the model, right? So in this case, in simple linear regression, we have 2 parameters, right? Because we have beta 0 and beta 1 in our regression equation, right? So how we find this, right? So we kind of went over this in module 0, right? But basically you will type in qt 1 minus alpha over 2 comma your degrees of freedom, which is n-2 for simple linear regression. So that's confidence intervals. What we also have is hypothesis testing. So hypothesis testing is basically to test whether a parameter is equal to a specific value or not. So in the context of simple linear regression, we usually want to test whether the slope is 0 or not, because if the slope is 0, there's no linear relationship, right? So if you think about drawing a picture, right, of your x and y variables, right, if the slope is 0, it means that it doesn't matter what the value is for your x variable, the y is always the same, right? So that's normally why we normally are testing whether the slope is 0 or not. Right, simple steps, state the null alternative. So I did mention it's typically null is saying that the slope is 0, the alternative is saying the slope is not 0. But based on the context of your problem, it might be a different value over here. We then calculate a test statistic, right? And then we make a conclusion, right, based on either the critical value or the p-value approach. The test for the slope is a t-statistic. So the framework is the statistic, which is the sample slope. This is just a value in the null hypothesis, so usually it's 0, and this is the standard error of the slope. So typically, so I should maybe have written here, typically these are the tests that we want to do, right? And the t-test allows us to test this. Now, there could be a situation where you would want a one-sided test. You might also have a situation where this value in the null is not 0. And is a value other than 0. You could actually test it, but as I say, typically this is the hypothesis of interest, right? And that's the test statistic. So if your null hypothesis was a value other than 0, then that you have to replace this value over here. Critical value approach, right? If your magnitude of your test statistic is larger than the critical value, and the p-value approach, right? So if a two-sided test, if your p-value is less than alpha, we reject the null hypothesis. So a lot of these things, I'm kind of going over these pretty quickly, right? Because we've seen this in module 0. Right, so critical region, right? We can type this in to find the critical region for a two-sided test. How does this change if we have a one-sided test, right? So if it's a one-sided test, we are typing QT of 1 minus alpha rather than 1 minus alpha over 2, right? Because alpha is on one tail end rather than splitting alpha into two tail ends. A couple of notes: conclusions from a two-sided test and confidence intervals at the same significance level are always consistent. They will not contradict each other. Another note, the p-value approach and the critical value approach will always lead to the same conclusions as long as you're performing the test at the same significance level. In simple linear regression, but there's also an ANOVA F test. The ANOVA F test tests the null and alternative specific. It's only this combination of null and alternative, right? Whereas in the t-test, you could test a two-sided test. You can give a one-sided test, or you could have a test where the null is a value other than 0. So only in this setting, right, where the null alternative is 0 and not 0, then is the ANOVA F test and t test the same in simple linear regression. The formula for the ANOVA F test is mean square regression over mean square residual. Again, if you're doing the same test for both the F and t test, it turns out that the F statistic will be the square of your t statistic. They will be numerically equal to one another. The F test is then compared to an F distribution with, so notice that the F statistic is a fraction. So there's actually what we call a numerator degree of freedom and a denominator degree of freedom, right? So the first one is for the numerator and the second one is for the denominator. So the degrees of freedom is 1 and n minus p. So let's just take a look at some R output. So this is the same data set that you saw in the tutorial. So just a few things to mention, right? That value over here, 11.8, that's beta 1. This under standard error, right? That's the standard error of beta 1 hat, right? 3.485. This is the t statistic. So this t statistic, so all these tests that you see in R, right, is testing whether the slope is 0 or not. Right, so if you want to test a test other than these two, then right, suppose you don't want to test whether it's 0 or not, but maybe say whether it's 5 or not, then you have to calculate that on your own. Test statistic, right, the estimate, beta 1, minus the null value, which is 0, divided by the standard error, 3.8485, and you work that out. That should give you this 3.386, right? So that's how that's found. P-value over there. So if you type in, right, to find a p-value on own, you should get that result, right? So a two-sided test, 3.386. We want area to the right of that and area to the left of negative 3.386, right? So if you type in QT, negative 3.386, degrees of freedom over here is 18, right? So I know that because that's n minus p. And you multiply that by 2, that should give you this value over here. So that's the looking at the t-test for the slope. And one thing I mentioned, right, the F statistic, it's over here. And I say that the F statistic is the square of the t statistic. So if you square this value, 3.386 over here, you should get this value over here. Right? Notice that the p-value here, p-value there, exactly the same, right? Because as I say, in simple linear regression, with a two-sided test where the null is 0, the t-test and F test will give you the exact same results. Moving along, we'll talk about two more intervals that we see. So the next two intervals are based on the two interpretations one could have of y hat, right? So this is the regression equation, the population, and that's the regression equation, the sample. So there are two potential interpretations of y hat. You could say that y hat estimates mu y, which is the mean of the response for specific value of x, right? So I submit a value of x, what's y hat? Or you could view y hat as a prediction for the value of the response for a specific observation of x. So first interpretation, the average of the response. Second one is the value of the response for an individual. So depending on which interpretation you're interested in, right, you would want one of these intervals. Right, so if you want to find the interval for the average y for a specific value of x, so x naught here is just a symbol to represent a specific value of x. Right, the point estimator is basically from just subbing in x naught into your regression equation. And then this is your confidence interval, right? So in this setting, that's the estimate, that's the multiplier, right? And this whole chunk here, right, is the standard error of the estimate, right? So it's still the same framework, but the formula for the standard error now changes because it's now the standard error for this quantity rather than the slope. Now, if you're interested in the second interpretation, right, an interval for a new value of y when x equals x naught, this is called a prediction interval for a future observation y naught. So prediction interval for y naught takes into account two sources of variation. One is the variation in the location for the distribution of y. So basically, where is the center of the distribution for y? So it's basically saying, right, the variation associated with your regression equation. But there's an additional source of variation when you're talking about an individual observation, is the variation within the probability distribution of y, right? So the idea behind this is that, right, we write our equation as yi being equal to beta 0 hat plus, so this is in the sample, beta 1 hat xi plus your residual. Now, if you're looking at the average response, the sources of variation come from beta 0 hat and beta 1 hat. But when you're talking about an individual value, you have the variation from your intercept and slope, but also from your residual. Right, so this is the additional source of variation that comes in, whereas in the previous interpretation, right, it only takes into account bullet point 1. So the prediction interval, right, estimate, that's y hat, multiplier, and that is the standard error of y hat, the estimate, right? So that's the standard error of the estimate, which is that over there. Right, and if you compare equation 3 with equation 2, right, the standard error for the mean response is equation 2 is basically summation xi minus x bar square, right? There's this additional one here, right? This is to account for the variance associated with considering the errors. Right, so the prediction interval is always wider. There's more uncertainty in individual observations. So this is just a graphical representation of the two types of intervals, right? So this black dots represent the data points. So it's basically summer temperature in two different towns. The black line represents the regression equation. The blue bands represent, right, so for each value on the x-axis, I calculate the lower and upper bound of the confidence interval for the mean response. And so the blue, that's what the blue line represents. So notice the blue line tries to capture where the line is, right, because it's just trying to find the average, right, which is the line. The prediction interval is in red, so it's basically, again, for each value of x, I'm computing the upper and lower bound of the prediction interval and overlaying those two lines. The prediction interval is trying to capture the individual data points, right? So that's why it's much more further spread apart compared to the confidence interval. Right, so we've kind of gone over, right, the 4 different inferential procedures that we've seen: confidence interval for the slope, hypothesis testing for the slope, of which there's the T and ANOVA F test. We talked about the confidence interval for the mean response, and we talked about the prediction interval for a new response.